Hello and welcome, everyone. My name is Lauren Harrington, and it is my privilege to be the host of today's webinar. Joining me today is Dr. Brian Kloppenborg, the Executive Director of the AAVSO. Brian has a wonderful presentation lined up for us, but before we get started, I do have a few quick announcements which I'd like to make. First, I would like to point out a few features right here inside of Zoom Webinar. If you take a look at the bottom of your Zoom window, you will see a few different buttons. There's the chat box where we've been swapping our Aurora stories. And there's also a show captions button, which allows you to enable or disable Zoom's automatic closed captioning. And finally, there's an extra button labeled Q&A. When you click on that Q&A button, you will have the option to submit questions for our speaker. You can submit as many questions as you'd like at any point during the presentation. Don't worry, it won't interrupt the instructor. After the presentation, we do have some time set aside for a Q&A, and we will try to answer as many of your questions as we can get to. Now, I have some exciting news. Next month, we are running a special mini-series of webinars focused on the AAVSO's special interest groups, known as sections. We'll begin on June 1st with a webinar spotlighting the solar observing section, the eclipsing binary section, and the long period variables section. And I'm just going to say, if this ongoing solar storm has got you excited, you really do not want to miss the presentation from the solar section on June 1st. You can learn more about this upcoming mini-series and find registration links on our website at aavso.org/webinars. Now, I would like to thank our 2024 series sponsor, Boyce Astro. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please check out their website to learn more about their work. I would also like to thank this webinar's sponsor, Chroma Technology Corporation. Founded in 1991 as a 100% employee-owned company, Chroma Technology is a leading manufacturer and OEM supplier of highly precise optical filters using thin film coating technology. Chroma Technology stands out in the field of astronomy for its unparalleled expertise. Their optical filters are designed to not just meet, but to exceed industry standards, ensuring superior performance and durability for years to come. All right. Our speaker today is an AAVSO celebrity. I think that's safe to say. You all know him as the executive director of the AAVSO. What you may not know is that he earned his PhD in physics from the University of Denver. And before he joined us here at the AAVSO, he spent 6 years working as a research scientist at Georgia Tech Research Institute. His research interests include eclipsing binaries, novae, and young stellar objects, which he studies using a mixture of spectroscopy, astrometry, long baseline optical interferometry, and, of course, photometry. When it comes to photometry, he's honestly an unrivaled expert, and that's because our speaker has done it all. He's been a backyard observer, a researcher using AAVSO data, and he served on last year's Data Quality Task Force Committee. Together with the others on the DQTF, he evaluated the state of the AAVSO's database and identified concrete ways in which we can all push our data to ever greater levels of precision. Today, he's here to teach us all about filters and transformations and how you can leverage these tools and methods to uncover stellar phenomena and significantly improve your photometric accuracy. This might just be the most important presentation that you watch this year. So, without further ado, I would like to introduce the Executive Director of the AAVSO, Dr. Brian Kloppenborg. Welcome, Brian.
Yeah, Lauren, thank you very much for that wonderful introduction. So I'll go ahead and start sharing my slides here and pop over to the other screen. So you should see them right about now. Is it working for you, Lauren?
Looks perfect.
Oh, terrific. All right, so as Lauren mentioned, I'm Brian Kloppenborg. I'm the Executive Director of the AAVSO, and thank you all for attending today's talk discussing filters and photometric transformations. So as has become my tradition for being out in industry, is I'd like to present you a bottom line up front so that you can sit back and relax and enjoy the rest of the talk. And so the first point here is that your equipment and observing conditions really do make your observations unique. And because of this, you really do need to be using filters to help standardize your measurements. But even if you use filters, there are still going to be some slight differences. And I'll actually walk us through the physical processes here to demonstrate that effect. The way that you correct for these small remaining differences is to apply a variety of different photometric transformations, and that brings your data all into a consistent reference frame that's just outside of the Earth's atmosphere in whatever photometric filter that you will be looking at. Now, I will caution y'all that this is going to be a pretty theoretical talk. I want you to understand why you should be why you should be using filters and why you should be applying photometric transformations. And if you'd like to see kind of a practical applied version of this for like how you actually go about applying filters, if you put them in your filter wheel, you're good to go. But if you want to see how to apply transformations in the AVSO's YouTube channel, there's a talk by Tom Calderwood and also a talk about George Silvas about how to actually apply some of the theoretical aspects that I'm going to be discussing today. And that'll help improve your quality of your data. Now, right before this talk, right before we came live, I was mentioning to Lauren that this talk took me a long time to assemble because of a variety of different things that I didn't know I was going to encounter. And so I have to put in a couple of disclaimers up front. In order to make some of the physical effects that I'm going to show you visible, I had to break a few rules. The first of which is I'm going to be using some data where it doesn't quite apply, but it's probably close enough for illustrative purposes. And so I'll point out when that actually occurs. That's a one-time thing, but it propagates through almost all the rest of the presentation. Being a physicist by heart, some of the physical constants in various equations magically became one. That simplifies the math a little bit and also allows me to scale things a little bit more uniformly so that I don't have to deal with some of the intricacies between looking at different photometric systems and different units of measure effectively. In many of my slides, I have intentionally ignored units or dropped them. Usually you wouldn't want to do that, but for illustrative purposes, I think it's actually perfectly fine. And then lastly, throughout this presentation, there'll actually be a mixture of both relative and absolute flux scales. And so I would just let you know that I've applied absolute flux where it is needed and basically left everything else as relative flux for the rest of the talk. So let's first talk about the journey of a photon. And so if we just take a look at the pictures here and work from the left side of the screen over to the right-hand side of the screen, a star out there someplace in space is emitting photons due to a wide variety of physical processes, which we're not going to discuss today at any length. But as those photons journey from the star down to your detector, they pass through the interstellar medium, they pass through the atmosphere, they interact with your optics. They may be attenuated or completely blocked out by a variety of different filters that you may have in place. And then finally, your detector actually does something to the photons as well, because they all have different characteristics of what light they can pass. And because of that, almost all of this talk is going to be looking at spectra and the impact of each one of these devices or each one of these physical phenomena on spectra. And then finally, we'll sum up the spectrum and present a total number of photons that we might count in each one of these situations. So first off, let's take a look at a couple of different stars to see what they might actually look like in a spectroscopic sense. So all of these plots along the vertical axis is some measurement of flux, and on the horizontal axis is a measurement of wavelength. Now, a fairly standard, relatively clean star, if you want to think about it, is this A05 star that's shown on the left-hand side. You can see these large icicles that are hanging down on the left-hand side. These are actually absorption lines being caused by hydrogen. And then this relatively smooth shape that exists here, that's more or less the continuum emission from there. Now, we're not going to talk much about spectroscopy here, but I will say that stars have a wide variety of different spectra, which means that they're also going to have a wide variety of photometric measurements that you can get from them. So if you compare the A05 on the left-hand side of the screen with either one of the stars that you see on the right-hand side of the screen. For example, this star here, which I will say I asked Lauren to give me some interesting stars that I may not know, and she definitely succeeded in that job. So she gave me a spectrum here of a system that shows a copious number of emission lines all across the whole spectrum. And then down here is a relatively hot star where a lot of the band head and the drop off that you would see on the left-hand side is not actually being represented because it's off to the left-hand side of the spectrum that's represented there. But so I'm going to spend all of my subsequent slides are going to be looking at this A05 spectrum. I'm going to use that as my basis. But you can imagine that if we were to apply the techniques that I'm going to be discussing to either one of the two cases on the right-hand side, we could get fairly different answers depending on exactly what star we're looking at and what system we're using to observe it with. Now, after the photons leave the surface of the stars, they travel for a long period of time through space. And while we would like to think that space is actually completely empty, it's not. There's all sorts of things that are out there. There's tons of hydrogen that's floating around. There's areas that are relatively dusty. And so, there could be, clumps of various dust grains. There could be molecules floating around in space. It's a pretty interesting world out there. And so on the left-hand side, I've shown you a galactic plane view of absorption due to the interstellar medium. And as you might expect, there's lots of dust that sits in the galactic plane. So along the vertical axis here is plus or minus 10 degrees from the galactic plane, and then plus or minus 100 degrees from the galactic center on the horizontal axis. You can see here, there's the Cygnus X region. There's, of course, the Milky Way center there. There's all sorts of really interesting things that are here. But you can notice that when you get towards the kind of, the edge of the galactic plane, there's not a whole lot of absorption that's out there. But when you get towards the center of the galactic plane, there's actually a fairly substantial amount of absorption that can occur in those regions. And that absorption is not uniform across the spectrum. So on the right-hand side, this plot, the way that it's displayed is it shows the amount of absorption on the vertical axis versus wave number on the horizontal axis. And I would have just flipped this plot around, but it probably wouldn't make a whole lot of sense. So I would encourage you to look at the vertical, the scale on the top here, where you go from about 120 nanometers or 1,200 angstroms over here to about 600 nanometers or 6,000 angstroms. So kind of covering the UV spectrum and out to the optical. And you can see here that at ultraviolet wavelengths, there's a lot of absorption that occurs. There's a bump that sits in the middle here, which I'm not going to discuss what actually causes that, but you could look at this paper by Phil Patrick if you'd like to. And then absorption drops off as you head out towards the infrared wavelengths. So as photometrists, we don't attempt to correct for this. And that is intentional because it's complicated, right? On the left-hand side, you see that absorption varies based upon where you're looking in the sky. And on the right-hand side, you see that absorption varies as a function of wavelength. And as you can see, even the graph on the right-hand side, there's 3 different curves here. So in 1999, there was a couple of different ideas of what the actual physical properties of the absorption was. And so there were different models. A lot has evolved in this particular field since then. And therefore, our understanding of interstellar absorption is growing, and therefore we don't attempt to correct for it. And I'll tell you exactly kind of where we stop on that bound here in just a minute. Now, Earth's atmosphere is also something that causes changes to the light that comes from outer space. So here I've shown solar irradiance. Now there's 3 different lines that are plotted here. Again, on the vertical axis is some arbitrary unit of flux, and on the horizontal axis is wavelength with longer wavelengths off to the right-hand side. The green line here shows basically what a black body radiation curve would look like at about 5,700 Celsius. Now I've intentionally caused a few things. I've played with the units a little bit here to kind of make things match a little bit more closely. So that's not really what the black body spectrum is, but I put it this way so that I could normalize the flux out a little bit. Now, so the irradiance of the sun at the top of the atmosphere is this red trace. And you can see that when you go from the top of the atmosphere to down on the Earth's surface, you have a lot of light that's get lost here kind of in the 500 nanometer range, just simply because the atmosphere absorbs it. A lot of that is actually due to atomic or molecular oxygen. You can also see that there's a variety of large dips that appear from the red line down to the blue line. Almost all of these are caused by other molecules, mostly water vapor and carbon dioxide. And so we'll come back to exactly how we can use these things to our advantage here in a little bit. Now, in addition to the atmosphere, your optics also have some impact upon the flux that you're able to measure. Fortunately, most optical surfaces that we use, at least at optical wavelengths, are pretty reflective. And so on the left-hand side, I've pulled up a transmission curve for shot supramax glass. And on the right-hand side, I've plotted a reflectance curve for aluminum that has a coating on it so that it doesn't actually experience much oxidization. If your mirror is not coated with some form of protective coating, it relatively degrades pretty quickly, and so the overall reflectance drops relatively fast. But you can see here that the total amount of transmission through the glass over most optical wavelengths is pretty high. It's kind of in the upper 90%-ish. And the same thing goes for this for the reflectivity off of this particular mirror. It's relatively uniform. However, if you were to go off to the ultraviolet side with the glass, eventually the glass starts blocking ultraviolet light. Or if you go out a little bit in towards the more longer wavelengths, you can see here that you lose a little bit of flux, not a whole lot. It's just a couple of percent out here around 800 and 900 nanometers for a mirror. And so, your optics and anything that you have in your optical train impacts that as well. And then finally, there's the detectors. And I don't want to ignore our visual observers. Most of this talk is going to be focusing on some form of a digital detector, but I would like to say that the eyeballs are actually very good detectors as well. And so a little bit of biology up on the left-hand side is we can describe the different regions of your eye that are photosensitive in different ways, from the fovea, which is near the middle, the parafovea, and the perifovea, and then the macula that extends out further out to the outside. And then on the right-hand side, you can see the spectral response of these different regions of the eye as measured by a nice journal article by Hallett back in 1998. There was in the Journal of the AVSO. And you can see here that your peripheral rods are relatively sensitive to blue wavelengths, and then they fade off fairly quickly, whereas things that are near the center of your eye are a little bit less sensitive to blue and a little bit more sensitive to red. And the paper by Hallett actually gives some really good techniques for visual observers to overcome those particular effects that are known in our eyes. I will say that I was chatting with Sebastian about the actual practice of applying them, and he said that it is a very difficult thing to learn and practice and to apply relatively consistently, but he was able to improve his visual photometric estimates quite considerably once he took these things into account. Now, outside of eyeballs, one of the older types of detectors that we've had has been photodiodes. And so I pulled out the photodiodes that are located in the Optec SSP3 and SSP4 photometers, which are the ones that are most commonly used within the AVSO. And I'll only be talking about the SSP3 from most of the rest of the presentation, but we'll just take a quick journey over to look at the SSP4 in a moment. But we can see here that just kind of grossly speaking, the SSP3 is not quite as sensitive in terms of its overall response to blue wavelengths compared to red wavelengths, where it's actually about a factor of 3 more sensitive. And so this effect actually will impact the way that you measure light coming out of these systems, as I'll show in a few more slides. Now, the SSP4 is a relatively unique device within the AVSO because it actually is capable of measuring photometry in the J and H bands. Not a whole lot of folks, at least within the AVSO, work in that range. I think there was maybe fewer than 15 of these SSP4 units that were even built, and the AVSO has 5 of them. You can see something fairly similar if you can think in the infrared, right? This photodiode is a little bit less sensitive to the bluer end of the infrared spectrum than it is over to the redder end of the infrared spectrum. So, it'll have a slightly different response to each of those extremes. Now, CCD and CMOS sensors, so we'll branch over to two-dimensional detectors. So I pulled up the relative response curves to an older CCD that had one of these Kodak sensors in it versus a modern Sony CMOS sensor. And so in blue, you can see that the CCD here is a little bit less sensitive in the blue regions compared to what the CMOS sensor is. And the CCD sensor is actually more sensitive in the red than what the CMOS sensor is in similar regions. Now, mind you, normally you would plot this out in terms of quantum efficiency, but to make it a little bit more fair, because you end up normalizing things out when you reduce your spectra, you reduce your photometry anyway. I plotted them here with a relative response instead. Now, you might be wondering, okay, well, what about monochrome detectors versus color detectors? So under the hood, most color sensors are CMOS. There were a few color CCD detectors that were actually made. I have one of them here, actually. But you can take a look at the sensitivity here of the Sony sensor, which is, again, just a monochrome CMOS sensor, and compare it with the Sony IMX 575 in red, green, and blue. So red being, the red points here off to the right, green being in the middle, and blue being on the left-hand side. And if you've asked me a question about, hey, can I use red, green, blue sensors to do photometry? I'll say yes, absolutely, but please include an infrared block filter. And the reason for that is that despite the fact that blue covers blue wavelengths and green covers green wavelengths, in addition to that, the detectors have a fairly strong infrared leak that starts to appear kind of around 790, 800 nanometers. And so if you're measuring something that's in green, which is fairly similar to Johnson-Cousins V, you end up getting something that's more like green plus I rather than just, sorry, more like V plus I rather than just, V alone. And so if you put something in place, around 750 nanometers or something that blocks off everything to the right-hand side, then the green channel is fairly close to V, and the blue channel is relatively close to B, although they're not quite perfect. And then finally, let's just talk about color CMOS cameras in general, right? So you would think that green is green, right? Well, here, again, I've plotted the Sony IMX CMOS sensor and then two different other Sony sensors. One of is the IMX 585, which we saw just on the previous slide. And then there's the IMX 462 sensor. And you can see here that even within the green, there's a slight difference of probably about 10% in terms of its sensitivity at the primary green wavelengths. But once you get out into the near infrared, if you don't have that infrared block filter in place, you could be looking at maybe, like an 18 to 20% increase in sensitivity at any given one of these regions. And so the IMX 585 is one of these so-called deep well CMOS sensors. And so it's intentionally more sensitive to the infrared than what the Sony IMX 462 is, which is a standard photoreceptor site. And so you can actually use this to your advantage. Like if you wanted a camera that's a little bit more sensitive, a color camera that's a little bit more sensitive to the infrared, you would probably pick up the 585 instead of the 462. So let's go ahead and take these things that we've talked about and put them together into kind of a big picture idea. So up in the upper left-hand side, I have a standard A0, A05 spectrum. Let's multiply that by what the atmosphere, the AM 1.5 spectrum. Now, that's not actually physically correct. Really, what I'd want to do is multiply this by the transmittance of the atmosphere, but it's relatively close in this particular situation. So I'm going to go ahead and do it anyway. And as you might expect, right, the atmosphere had a whole bunch of additional absorption lines. It had a bunch of molecular absorption lines. And so we see here in the middle between hydrogen alpha and hydrogen beta, we get a bunch of additional telluric lines that are introduced within the spectrum. Now, if we add in the optics to the system, there's not really a whole lot of change because the optics, as you saw, are relatively flat in terms of their spectral reflectivity or spectral transmissions. It's kind of at the order of a 2% effect, so it's not very visible on this plot here. But then if we go from just having the optics to introducing the CMOS sensor, you can see here that the two peaks that appear, I guess that's alpha, the third and the fourth series of the hydrogen absorption bands. You can see here that there's actually been a dip in terms of the total amount of flux that's been delivered simply because the CMOS sensor is a little bit less sensitive on the blue end than what the optics are capable of providing to the camera. And so every single one of these optical components we put in the way alters the light that we're actually receiving at our detector. Now, here's kind of like the money shot. It's, well, let's compare a photodiode to a CCD to a CMOS sensor. And again, this is our same A05 spectrum. On the left-hand side, we have a photodiode. In the middle, we have a CCD camera, and on the right-hand side, we have a CMOS. The most obvious thing that you can see here is there's large differences in the amplitude of the spectrum that comes through. That's mostly just due to the quantum efficiencies of the different sensors. So this is one of my few plots where I actually pulled in the QEs and used them relatively directly. Now, the good thing is that you can normalize this out when you do your photometry, so it's not a large difference. The fact that the photodiode may only be getting about 20% of the flux, whereas the CCD sensor is twice as sensitive, and the CMOS sensor could be 3 times as sensitive, right? There's a lot of scaling that's come in here, so don't take these numbers as absolute, right? There's a lot of different factors that come into play here, but in this situation, that's kind of the trend that's looking to be. What I would like to call your attention to are the boxes that I've drawn here. So on the far left-hand side, you can see the red rectangle that follows the longer wavelength portions of, I should say, the Rayleigh Jeans region of the spectrum, right? It looks basically like a line in the continuum heading down through here. And so it's a fairly flat response during that region. But if you compare that with, say, like the CMOS sensor, you can see the spectrum is relatively curved. Likewise, if you were to compare the CCD sensor to the CMOS sensor here to the left of some of these hydrogen absorption lines, you can see that this little region here, kind of around just longward of 4,000 angstroms, versus the next hydrogen, the next peak between the two hydrogen lines here. Compare that with what we see over here on the right-hand side. You can see the more blue-word hill, if you will, is a little bit more attenuated in the CMOS sensor because it's less sensitive there in the blue wavelengths. So you can imagine that these sensors are going to be producing kind of different results. Now photometers, they have spectral sensitivity, but what they do is they count photons in the end, right? Either photons or photoelectrons. And so on the left-hand side, the total amount of flux that's under this curve is about 20,000 counts. In the middle, we have 35,000 counts, and on the right-hand side, we have 37,000 counts. And so just in terms of raw flux, we're getting very different measurements. And so for that reason, we need to introduce some additional controls. So the takeaway from here is that your equipment and observing conditions make your observations unique. If you have a different atmosphere above you, if you have a different camera, if you have different filters, it changes how the light works. And so you need to not only take the measurements, but also do a little bit of additional processing so that you can be consistent with other observers. Now, I haven't talked about photometric filters yet, and I think it's about time that we introduce them. So first off, what do photometric filters do, right? So they're really formed around 3 primary objectives, one of which is to continue consistency with previous photometric systems, and I'll mention one of those cases just in a second. Some of them, they avoid atmospheric absorption bands, and then other ones are designed to measure specific astronomical things. Now, we're most familiar with the Johnson's UBV and Cousins RI system, but I work out in the infrared mostly, and so I'm used to this particular JHK system that I mentioned on the right. But there are lots and lots of different photometric systems that are out there. So in addition, you probably know not only about Johnson Cousins, but you also know about Sloan. But there's something like 160 different photometric systems that are in the Asiago photometric database that have a wide variety of different purposes. There's actually a really good paper by Bezel in the 1990s where he enumerates all of these different photometric systems and talks about how some of them are highly optimized for stellar astrophysics, but they're not very good for galaxies. And so we've come to some kind of an agreement that as an astronomical community, that the Johnson Cousins system and the Sloan systems meet most of our use cases. For today's talk, I'm only going to talk about the Johnson Cousins system, but we will, if people are interested, we could talk about the Sloan system, or I could put up some posts on the forums to elaborate on them. So what about the UBVRI JHK system that Johnson's originally made, but then was modified by a couple people after that? So the U filter is really designed for astronomical purposes. The B filter mirrors quite closely the spectral response of photographic glass plates. So this is one of those things that's trying to continue a previous photometric system. V band mirrors the visual bandpass of what your eyes can do. And so this is a continuation of that as well. R and I are designed for astrophysical purposes, and JH and K are really meant to maximize the amount of flux that occurs between different atmospheric windows. Now, visualizing these, on the left-hand side, we have that same A0V star with Johnson's UVV filters and Cousins R and I. And you can see here that the U filter lives off to the left-hand side of the hydrogen bandhead. Is that the Balmer jump, Lauren? Again, I work out in the infrared, so
Yes, it
I
is. You've
wish.
got.
Yep. All right, there we go. So I'm usually way off to the right in these figures, so trying to remember what happens on the left is hard for me. And so the U filter measures photons that come up to the left of the Balmer jump. The B filter here measures quite closely with photographic glass plates, but it also measures what's happening to the right-hand side of the Balmer jump. The V filter is fairly well positioned here between hydrogen alpha and hydrogen beta, so it measures a pretty good chunk of continuum that sits between those two regions. And then R and I are off to the right-hand side, and I think they're made to kind of take advantage of various astrophysical processes plus atmospheric band passes. I did mention the JH and K systems, and so I wanted to illustrate on the right-hand side where they fit in. So now we're showing in the background of this plot is the solar transmittance spectra at the Earth, which is often called the AM 1.5 spectrum. And you can see here that there's 3 atmospheric band passes that exist out in here, and the J, the H, and the K filter, which are shown as these gray bands in the background, align really well to those. And so they're attempting to maximize the amount of flux that can go through there. Now, there's been modifications to the JHK system, like there's a K short, for example, but we aren't going to talk about that today. I will note that when I was creating this presentation, the I band here looked a little bit short to me. I thought it was actually further off to the right-hand side. And when I pulled up some other filters, I actually found that I think the reference that I used for the Cousins R I filter is wrong. So don't take my word that this is actually what I band looks like. I think it could be wrong here. So now, even if we put filters in place, there are still going to be differences, right? So here is that exact same A05 spectrum that I showed you, but now with both a photodiode, a CCD, and a CMOS sensor, but now we've applied a photometric V filter to it as well. So on the left-hand side, we can see that the photodiode, it's pulling out light in the right region that you might expect. On the right-hand side, the CCD and the CMOS sensors, they look like they have, like the overall shape is relatively consistent between them. And if we sum up the total amount of flux that we get in this situation with the photodiode, it's only getting about 57% of the flux that the CCD sensor gets. On the right-hand side, the CMOS sensor is getting about 99.7% of the flux that the CCD gets. And for this specific star, the specific filters, and the specific optical setup that I generated here as part of this theoretical system is that they're different, right? And fortunately, these are all differences that we can correct for now that we've picked out a specific bandpass of light that we want to pay attention to. So just keep in mind again that your equipment and your observing systems really truly make your observations unique. And in this system, it's the exact same star, the same atmosphere, the same optics, the same filter, just different sensors sitting on the right-hand side. And so, it's about as clear cut as you can get without actually going out and doing some real measurements to confirm. Now, because Chroma sponsored this webinar, I thought I'd pull up a few of their filters because we often get questions about their classic bezel their bezel filters versus their classic filters. So here you see the Johnson Cousins UBVR filters shown in the background as these colored bands. I've left off I again because I think my reference for an I filter was incorrect, not because there's anything wrong with Chroma's I filters. And then in the foreground, I plotted the equivalent of the Chroma bezel U versus the Chroma bezel classic, and then BVRI or BVR off to the right hand side. And just by visually comparing, you can see that these filters are different. And I will say that every filter that comes from a manufacturer is going to be different from the adjacent filter unless they're really close to each other when they're built. And so you get one filter from one lot versus another filter from another lot. They're going to have slight differences. And so, this is something that's to be expected. But I believe in both cases, both in case of the bezel filters and in case of the classic filters from Chroma, both of them have been shown to transform very well to the standard Johnson-Cousins system. So there's a quick reference there. So what we attempt to do when we do photometric transformations, so we just saw that even if we're taking data with identical systems or nearly identical systems, we're going to get different answers. And so to correct for those, we apply a process called photometric transformation. And what we attempt to do is back out the effect of the atmosphere, our optics, our filters, and our detector to put us outside of the atmosphere, still observing through the same photometric filter. So notice that we don't attempt to correct for anything happening at the star. So like the great dimming of Betelgeuse with that dust being belched out into space, we're not going to try to correct for that dust. We're also not going to attempt to correct for the interstellar medium. We just want to try to get everybody so that they're producing measurements that are at the same place, which is just right outside of the atmosphere here. So you probably have seen this photometric transformation equation here, where it expresses the calibrated the catalog magnitude or your instrumental derived calibrated magnitude in relationship to an instrumental magnitude, a 0-point offset, a color correction term, and maybe one or two air mass correction terms. And you probably have seen this before. You might have actually implemented it before in some of your own work, but I thought it would be relatively illustrative to show where this thing came from to begin with. And I apologize that I'm not going to go into this in a whole lot of detail. I was hoping actually to use some data from my own telescope for this purpose, but unfortunately it's been cloudy here the last several weeks and I wasn't able to get any data. So what you're going to be seeing here is theoretically generated data out of a spreadsheet, but it follows the exact same math and the equations that we've seen before. So how did we come up with this equation to begin with? Well, so if we take and we plot the instrumental magnitude that we're getting, so along the vertical axis here versus the catalog magnitude along the horizontal axis, we can see that there is a linear relationship between the two of them. So the very first thing that we're going to try to do is take this linear relationship, which doesn't intercept the y-axis at 0, and bring it back up so that it does intercept the y-axis at 0. That's called a 0-point correction. And so all we have to do there is just look at the delta between the 0 and here, and just basically subtract it out. And so what I've done here is looked at the 0-point correction and just brought my my curve and just shifted the whole thing vertically up by about 10 in this particular situation, using this linear least squares estimate. And you can see that the slope of the line hasn't changed between the right and the left from that coefficient, but just the intercept has changed from one to the other. And also the correlation coefficient hasn't changed. But now we brought it back up, so they should at least be lying on the same relationship. So ideally, this line should have a slope of 1, and it should pass through the intercept if our instrumental magnitude and our catalog magnitude matched precisely. The next thing that we look at is if we were to take and we would scratch our heads a little bit and we would say, all right, well, this line looks okay, but our correlation coefficient here is at 0.95. Maybe there's some other physical effect that's happening here that we would want to explore. And so you would take the data and you would plot it in a variety of different ways. And one of the ways that you might try is looking at color to start off with. So we can plot the color of our instrumental system versus the color of our catalog system, and we find out that it's actually linearly related. And so in this case, that's how we end up getting this B minus V coefficient, or B minus V value with a coefficient that sits out in front, is because there's a linear relationship between the color of the star and the data that we're getting from our instrument. And so once we derive from the slope of this line a color correction coefficient, which is C1 in this situation, it will actually improve the quality of our data. So on the left-hand side, we see that we have just applied our 0-point correction and we're getting an R squared of about 0.95. But when we apply a color correction coefficient, which in this situation, I didn't plot out what it actually was, but notice how the data go from being relatively scattered vertically here on the left-hand side to being much more tighter on the right-hand side. So it squishes everything back down and improves that correlation between the relationship between the instrumental magnitude and the catalog magnitude. And that's reflected by having this, relatively significant improvement in our color correction term. Now, you could keep going at this, and I'm not going to belabor that fact here in my talk, but you could also apply the color correction coefficient. You could find that there's a dependence upon air mass, and there's also a dependence upon the color time the air mass, which is the C2 and the C3 terms that sit there as well. Now, you might be wondering, how do we apply this in practice? Well, for photoelectric photometry, what you do is you observe standard stars relatively periodically. And then the good thing is that the reduction methods that PEP has been using for a fairly long time already have these things built in. And so that's one of the reasons why PEP photometry is always very consistent between observers. That and they're all using the exact same detectors that are built around the same time and the exact same filters, or at least relatively similar filters. And so they already have all of these things built in to their systems. On the right-hand side, if you're using like a CCD or a CMOS sensor, what you want to do is observe standard stars somewhat periodically, observe standard fields periodically, like M67, for example, is one of them that's a good one to observe. So most of the photometry software that's out there, it already does 0-point correction for you. So if there's like an ensemble correction or a synthetic star correction or something like that, what they're doing is they're taking all of the flux or somehow averaging out the flux of the stars that are there that have known magnitudes, and they're backing out what that 0-point actually is. And so the only thing that you have to do after that point is apply a color transformation coefficient. And one of the ways that you can do that is by using the AAVSO's color transform generator. And so you can find it at aavso.org/tg. It's a Python application which you can download onto your machine. It's actually an executable Python application. And then what it will allow you to do is look at your photometry of one of these standard fields, and it will plot out that color correction curve that I was showing a little bit ago that shows how your system responds to different colored stars. And what it will do is it will give you a color transformation coefficient. So you can apply that using either your own code by implementing the equation that I showed a couple slides ago, or if you happen to be a person that uses VPhote, there is the transform applier that's built into that, which actually ingests the data directly from the transform generator. And then lastly, back down to the lower left-hand side, there's also relatively wide field photometry that some people are doing, so several degrees in angular diameter. That's often like what you would see from like a DSLR camera. And so the thing that we've done when I was on the DSLR photometry team for the Citizen Sky program back in 2009 or so, we made a spreadsheet that actually takes into account that photometric correction equation that we saw just a few slides ago, and we built it into a spreadsheet that allows you to reduce your data. And so the general advice here is that what you want to do is orient your camera so that you bracket your science object with stars that span both magnitude, span the variable star both in magnitude and also in color, and then reduce those data using the DSLR photometry spreadsheet. And that allows you to back out all of those different effects. And so, just a little bit of practice. But in addition to this, you can go back and refer to some of the slides that, or some of the presentations that have been previously posted on the AVSO's YouTube channel. And so I think that's actually my last slide, Lauren. And so happy to take questions from the audience and talk a little bit more about photometric transformations and filters.
Fantastic. Bravo, Brian. That was excellent. So I see that we do have some questions here. First one here comes from Yogesh Shaban, who is curious about your opinion on the multi-filter approach for photo Z determination, which is used in the JPES survey.
That one, I haven't actually read what they're doing there, so unfortunately, I don't have an opinion on that one.
Okay.
It's often very, like, generally speaking, the more you sample the spectrum, the better you can characterize your instrument. And so I would guess that they're probably taking a reasonable approach, but I'd have to go read the paper instead.
Right, makes sense. Okay. All right. Another question here. So is transformation something that is only necessary when you are working with color filters, or is it something that unfiltered observers should be doing as well?
It becomes a lot more difficult with unfiltered photometry. So if you recall those stars at the very beginning of my presentation that I showed, and maybe it's useful to bring those back up here, Lauren. So just give me a second to pop over to those slides, and we'll go clear back to the very beginning here. All right, here we go. So so with photometric transformations, it's relatively easy to apply when you're using filters because the bandpass of light that's going to the sensor is very narrow and very constricted. If you're not using photometric filters, then you have to deal with this, which is the full gamut of spectra that's here. So if you can imagine, let's take this emission line spectrum over here as an example. Um, if it's possible that say one of these emission lines, right? And I don't know, Lauren, is this H beta over here that's really lit up? Maybe
Yes.
H alpha is there and H beta is over here. Um, if you have the amount of light that's coming from H beta drop precipitatively, then you have much less light at those shorter wavelengths, and the way that your sensor responds to it is different. And so the number of photoelectrons that your system produces at those shorter wavelengths will be different than the number of photoelectrons that it produces someplace else. And
Mhm.
so it gets very difficult to calibrate unfiltered observations. And even the effect of going from like a relatively low air mass, say like looking at something directly at the zenith, to looking at something that's kind of near the horizon, right? You scatter away a lot of blue light. That's one thing that I didn't discuss as part of this is the air mass side of the equation. But you end up losing a lot more blue light, and so your sensitivity. Let's pop over to like one of these filter. Oh, it's not a good example. Let's maybe over here, down in the lower left-hand corner, right? Your flux on the left-hand side is going to drop quite a lot. And so you really, like in principle, you could apply transformations to unfiltered data, but you have to understand the full physics of what's actually occurring behind the scenes, and it gets very difficult to do. So it's there's ways that you can address this from a high level photometry perspective, but you really do need to know a lot about the photometric systems that are being observed or that are being used.
I see. Okay, thank you. All right, our next question here, this is an interesting one from Theory Mitivane, who asks, which photometric catalog is the best to use for when you're calculating your transformation coefficients? Would that be Gaia? Would that be something else?
Yeah, that's a good question. So every photometric catalog has its own problems. Even the AVSO's own APAS catalog, despite it being relatively consistent, is pretty good. And one thing that I read that was interesting in the Bessel paper, which I mentioned earlier, this is Bessel's 1990-ish work. Um, the photometric system that Landolt used is different. So he used UBVRI photometry, but he had a different set of UBVRI filters in his system. And so his photometry is also off a little bit from other photometric systems. And so I would say that the best photometric system or the best photometric catalog for you to calibrate against is one that is relatively widely used and is relatively respected by lots of observers. And if you go from if one observer is calibrating with one photometric system against one photometric catalog, and another observer is calibrating against another photometric catalog, you'll probably see slight differences between their observations because not only could there be 0 point offsets between those two photometric systems, but there could also be color offsets because their filters are slightly different. Now, the bright thing is that most of these larger catalogs have gone to fairly extreme measures to try to control any kind of systematic effects, and they're relatively consistent with each other. But you can still spot, especially in like the more blue and the more red extremes or stars that have large emission lines, you can often spot slight photometric differences. And
Mhm.
probably the easiest way to catch those is if you're plotting your instrumental magnitudes versus your catalog magnitudes, and you've taken into account your 0 point correction and your color correction, the stars that are way off from the line are either going to be variable or there's something wrong with the underlying photometric catalog. And so, if you're using a lot of different stars to calibrate against, you can usually pick those things out. Otherwise, try to be consistent with anybody else that you're collaborating with.
Good advice. Thank you. While we're talking about catalog data, there was this question from Leo Fernig asking about if you have any advice for comparing, if you are using Gaia magnitudes, how do you make the translation between Gaia G magnitudes and UBVRI so that you can understand what that relation is?
Yeah, so if you can give me just a second here. Lauren is smiling because this is a common question that our own staff has come up with several times. And so I'll take you to this page here on the web. So what I did was I searched for just Gaia color correction, and there's this paper in the Gaia archive called Photometric Relationships with Other Photometric Systems. And here they show the method of transforming between Gaia magnitudes and a whole bunch of other different photometric systems, including Tycho, Hipparcos, and Johnson Cousins. And so we'll just search for Johnson and find the figures. Here we go. And the reason why my screen was so large is because you have to blow up these figures to see what's actually happening. So we'll take a look here. Now, I showed you some pictures of instrumental magnitude versus calibrator magnitude and a nice linear relationship. In reality, that's not what you're going to see. And that was one of the simplifications that I had to make to make this presentation be a little bit shorter and a little bit more understandable. In the case of going from Gaia's photometric system, so like Gaia green to Johnson Cousins V versus the color of V minus I in the Johnson Cousins system, you can see here that their relationship between those systems is actually cubic. And so you apply this equation that's listed down here in the bottom portion of this figure to the color index becomes the X value, and then it predicts out the corresponding Gaia magnitude that comes out of here. And so they have that here for a variety of different Gaia, either the green or the red bandpass or the blue bandpass. And so this is probably one of the best references to go with. Now, the question that was just asked before this is, how do you know if a star is not really good? You can see here that, sorry, how do you know if there's a star that, the question was, which catalog should you be using? And I mentioned that there will be stars that will be wrong in that catalog. I would say that, these stars that are sticking up here high above the curve, they're either variable stars or there's something wrong with them in the other catalog that they used. And so by having all of these different sources cross-referenced against each other, we start to pick these things out, and the errors between them become a little bit more apparent. So again, if you want to find that, just do a Google search for Gaia color correction, and it's the paper that should come up in the search term. It's the photometric relationships with other systems or something like that.
Mhm. Perfect. Thank you. Okay, so pivoting topics a little bit now over to filters. So we've had several questions about filter sets. First, just a question from Tom Alderwelt, who asks, why is it that the Sloan UGRIZ filter is becoming so prevalent and replacing UBVRI Johnson Cousins, it seems? He's noting that it's getting harder and harder to find UBVRI filters to buy.
Yeah, and I don't know the full history behind that, and that might be a question that we would want to take over to Arnie in the forums. I do know that some of the original Johnson Cousins filters, so they were made out of glass, and the glass was I want to use the word doped, but that's for like semiconductors. But the glass had material in it that has been deemed to not be safe for people to handle. A lot of that older glass also had issues with. After a while, it was relatively hygroscopic, I believe, and it would start to kind of like haze up on the surface, and you'd have to treat it with acetone to get it back down to where you could see through it. And so that really led to kind of a not a lot of liking for those photometric filters. Now, since then, some companies like Chroma, for example, have produced thin film coated glass. So it's just glass with a layer that sits on top that mimics the bandpass of what you would get from those other photometric filters. But those photometric, these recreated ones don't match the original ones, and the original ones didn't match the original ones anyway. And so in either case, you have to do photometric transformations to get over to those other systems. Now, the nice thing with the new Sloan filters is they're relatively popular. I believe they first became popular because they're optimized for looking at galactic sources, and that's one thing that we should check with Arnie on the forums. And so they're not quite as ideal for stellar work compared to extragalactic work. But as astronomy, professional astronomers have shifted their interests over from stellar physics to galactic physics to extragalactic physics, and now they're coming back to stars via exoplanets. The filters that they are using have changed relatively considerably. So, my uninformed knowledge from just reading some different papers, I think that's kind of what's going on behind the scenes. But um, I would encourage the individual to ask that question in the forums, and I'm certain that Arnie and a couple other people who lived that era effectively would be happy to chime in.
Good advice. Thank you. And quite related to that, I think this one is worth reading out and answering explicitly. We had a couple different people asking specifically about, say you're getting UBVRI filters on the forums. So there are a lot of people who place stress on which particular brand is going to be like AAVSO approved, and this one transforms better and this one doesn't. Is that a thing, or does it really actually not matter as long as you're transforming?
So the AVSO has taken a neutral stance towards particular vendors for a variety of reasons. I've been talking with the board to see how much we can stretch our neutralness. I would like to have filters that are, some that we have evaluated and shown to transform, but at the same time, we also don't want to insult vendors that are producing things that are for a relatively niche hobby, namely variable star astronomy. And so figuring out how to walk that world is a little bit difficult. What I would say is what we have done historically is just go look at the papers and evaluate them to determine whether or not somebody has deemed that they are actually suitable. I will say that all the filters that I looked at as part of this talk, so I pulled up the original Johnson set. I pulled up the Cousins extension. I pulled up the bezel set. I've also pulled up, I have a pair of relatively old and obscure UBVRI filters, and there's also the different chroma sets that I showed here during this presentation. As long as you're applying photometric transformations, they work in the vast majority of situations. Now, there are probably a few instances where certain filters don't work for certain purposes. M stars, they're incredibly red. They may not work as well if the eye filter doesn't match somebody else's eye filter because it lets in a little extra light, or it doesn't let in as much light as something else. And so, I would encourage folks to go out and read the literature, and hopefully, with the board, we'll be able to change our perspective a little bit and provide official recommendations, or at least these are suitable for use statements from the AVSO.
Thank you. Okay, our next question here comes from Robert Stencil, who is asking about specifically for the case of follow-up in this era of large all-sky surveys. You'd mentioned that a large part of why you choose certain filters is for consistency with historical data. But if we're talking about newly discovered objects and you're doing follow-up on these, is there some other filter set that would be preferable? Assuming transformation can standardize to whichever system you need within errors.
Yeah, it may be advantageous to work in the same photometric system that the survey is working in. So if the survey is working in Sloan, it may be advantageous to work in Sloan. The nice thing is that professional astronomers understand these different photometric systems, and especially with the developments of AstroPi, they have a lot of built-in features that if you have like a Sloan G and a Johnson Cousins R, and you're looking to do spectral energy distribution fitting, the shapes of those curves are understood, and you can use them relatively easily from a professional sense. You can mix and match filters without a whole lot of issues. And so I would say if you already have filters, keep using them. If you're looking at collaborating with a specific sky survey, then perhaps you might want to consider purchasing those filters that are of that same system. Or in my situation, I actually got my filter secondhand from Bob Stencil, and so I just kept using what I have. So whatever filters match your use case the best are probably the ones to be using.
Okay. Thank you. Okay, so next we had a couple of questions about transformation with ensemble photometry. So if you're doing ensemble photometry, what changes in calculating your transformational coefficients? What do you do?
Yeah, yeah. So in to the best of my knowledge, all the photometric packages out there, when they do some form of ensemble photometry, they're basically just doing 0 point correction. So um, I don't remember which photometric packages do which. I remember as part of the data quality task force and the corresponding final report, we went through each one of them and we enumerated what they do. There's one package that it creates a synthetic star that is literally just the sum of all of the instrumental magnitudes for your calibration stars and the sum of all the catalog magnitudes. And so you get like a superstar calibrator. Another one, it averages those same quantities. And then another one, it does something different as well. There were like three primary ways that they explored things. But in these situations, as far as I am aware, most of the photometric software out there only does 0 point correction, but you want to take a look and see exactly what's happening under the hood. Now, the nice thing about doing ensemble photometry is if those photometric packages are already looking at all of those stars and they have the color information in addition to the catalog magnitude information, they could apply the whole photometric transformation equation that I just listed for you with the color correction coefficients that you've determined either from like the DSLR photometry perspective, where you get color correction and air mass correction from within the image itself, because the fields are so wide, you get a good sampling. Or in the case of CCD or CMOS photometry, where you have relatively small fields of view, you may need to determine them from other sources like M67, determine the color transformation coefficients, and apply them there. When you're doing ensemble photometry, really you have to look back and see exactly what's being implemented in your photometric package of choice to see what they're actually doing to understand what changes there. But more than likely, it's just 0 point correction.
Okay, thank you. Okay, so our next question here comes from Terry Dixon, who asks if there are any limitations optically based on the focal length or speed of telescope when you're using photometric filters. Like, is there such thing as a telescope that's too fast to use filters?
Um, that's a really good question, actually. So you can have some kind of weird things happen on really fast systems where if you think about the convergence of the light rays, by putting an extra piece of glass in there, it can cause the light to deviate from its normal path. Certainly, one thing that you can get is with fast systems, and actually even with my system here, which is an f6.3, you can run into situations where the filters are no longer parfocal, which means that each filter will need to have its own focus setting, which is not logistically, it's not really too big of a deal. Most telescope control software can change the focus for each filter. You can also end up with systems if their optics are a little bit too fast, that you might end up with multiple images on the sensor or something like that. But you'd really have to either you know do the ray tracing through something like Zmax, or just try it out and see what happens.
Mhm.
I'm not aware of any system that like the Celestron Rosas. They're relatively quick at like an f2, I think, and they have a specific place where you have to put the filter in, and it's usually just one filter at a time. And so usually the manufacturers have taken those sorts of things into consideration, and they'll say, you don't want to use a filter that's too thick, or you have to put in this specific place as opposed to anywhere within the optical train. So that might be another one of those situations where you'll have to go out and read the manual, or buy a specific filter holder for a specific optical system.
Mhm. Thank you. All right, so our next question here is actually related to calibrating DSLR data or color sensor data in general. Um, do you debayer the image before or after figuring out your coefficients and doing this calibration?
Yeah,
Do you have to take that into consideration doing transformations?
Yeah, so you with with any form of color sensor, whether it's a DSLR or a color CMOS or a color CCD, for those few that do exist, you want to debayer the system first and get individual red, green, and blue channels, because those red, green, blue filters are effectively, well, they're filters, right? And so you need to determine the transformation between, say, your green channel and V, or your blue channel and B. And provided that you don't have a bad infrared leak. So always debayer first before you debayer, and treat the filters, the red, green, blue filters, as if they were standard photometric filters like BVR, and do the appropriate transformations in that space with the images, color images channels separate.
Good advice. I think that leads in really well to our next question here, which comes from Brett Fadem, who says that he's very encouraged that he can do photometry with a CMOS and even with a color camera, and would like to know if we know of any good task lists breaking down the steps to follow in processing in each of these cases.
Yeah. So a starter point would be to take a look at the DSLR photometry tutorial. Now, I know that it says DSLR in there. There's a few things that are not particularly applicable, like allowing the stars to trail or defocusing the image slightly. But the image processing section in there, where it describes segmenting out the images into their individual color channels and then how to treat them independently, is a reasonable place to start in terms of learning about that type of photometry. Um, One thing that is different about the DSLR photometry spreadsheet, which is the data reduction tool that a lot of people are using for those images, and a more traditional photometry tool, is that when the spreadsheet was developed, we only used the green channel, and we didn't use B and R for a variety of reasons, which I won't discuss here. Basically, it was just green and V were really close, and at the time, B and red were not close to the corresponding filters. One assumption that we made was that for stars that change dramatically in color, so these will be like your Cepheid variables, for example, um, we just use the mean color as opposed to like a measured instrumental color at the time that the observation occurred. Now, that does introduce a little bit of additional uncertainty, but it'll be proportional to whatever your color transformation coefficient is for your system. So if your color transformation coefficient is like 0.01, it'll be an error no larger than 0.01 times the mean color of the system. So, potentially, 10 millimags or something like that. And it's not terrible, but it's relatively systematic, and it'll be pretty constant most of the time.
Okay, interesting, thanks. And speaking of color correction coefficients, we had a couple questions about that in particular. One is that when you are computing those and you subtract the B magnitude from the B magnitude, do you first need to convert the values to a linear scale since magnitudes are logarithmic values?
You should be able to work just in magnitude space. That's how most of these equations are written.
Okay. And this is somewhat tangentially related to the color coefficients topic. What if you only have a V filter and you can't take B data in order to produce color coefficients? Can you still do
Yeah.
transformation?
Yeah, you can still do transformation, and that's one of the cool things that we learned from that DSLR group back in 2009, is that if you assume a mean color for the system, uh, so um, uh, well, maybe I'll preface this before I go any further. So there's two things that you need to watch out for. One of which, don't look at stars that have very extreme color changes, because of the thing that I just mentioned a little bit ago, where you're assuming a mean color for the system, and usually that's okay. But if your color transformation coefficient is large and the swing in colors is also large, you'll end up with some kind of wonky values at the minimum and maximum color, because you can just assume a mean magnitude. So I would say that if you only have a V filter, you can certainly still do color transformations by assuming a mean magnitude. And you can take a look and see what's being done within the DSLR photometry group. That's probably the best way to do color transformations. But do keep in mind that the objects that you select need to be relatively benign in terms of their color changes. Or, if you're after you've submitted your data, go back and look at it and see how your data is performing. There might be some other way that you can apply another correction that is, say, dependent upon somebody else's color measurement or something like that. So there may be some ways to deal with it.
Mhm. Okay, thank you. And as kind of a follow-on question to that, we just had a question come in from Raymond Oltian, who asked, if you are studying a variable star which has significant shifts in color as well as magnitude, what should you do in order to accurately transform your data of that?
So in that particular case, make sure that you're getting more than one color.
Mhm.
So ideally, B minus V or V minus R or something like that, and use those use that in the rest of the color transformation equations. So what I showed today was really just what you would do for V, where you have a B minus V, but there is an equivalent formula for U band and R band and all of the other ones as well. I didn't put them here, but Arnie Hendon had a pretty good book that described how to do this, how to do the process of color transformations in the situation of CCD CMOS sensors. And I think Arnie's been working on a new book, which I don't know when it's going to come out, but those equations are relatively well known throughout the photometric community, and if needed, we can pull them out of a book and post them someplace.
Okay, thank you. Next up, we got a couple of quick questions that were related to particular software packages. It's okay if you don't know the answer to these,
Mhm.
we can go past them. But first was actually related to VPhoto, our software.
Mhm.
Um, do you know whether VPhoto has the capability to do transformations when doing ensemble photometry at this point in time?
VPhoto itself, no. However, there is the transform applier, which is
Mhm.
done after the VPhoto step that does the color transformation coefficients. And so if you search for transform applier AAVSO, there's a really nice web page that George Silva's put together that describes how it actually works.
Mhm.
And so the workflow there is you start off first by using, you observe your standard field, M57 or M67, for example, and then run that through the transform generator. That'll give you transformation coefficients, which then you enter into a page on VPhoto, and then VPhoto through the transform applier. After you're done with VPhoto, then you use the transform applier to apply the transforms to your data, and then it modifies the AEFF file that you use for submitting to the AVSO. So in that situation, the ensemble within VPhoto does the 0 point correction, and transform applier does the color correction, but there is no air mass correction that's built into VPhoto presently.
Mhm. Okay, thank you. All right, we're down to the last couple of questions here. So this one comes from Louis Barnio, who asks how to choose an appropriate standard field. It will obviously depend on what's the latitude of your observatory, which fields are accessible. Do you need to take into account the declination of the target?
So that would actually come in through air mass corrections. And so in my situation, I only have one choice because that's all I can see off to the north. And so that's the only field that I actually can use for doing to observe for calibration coefficients, for example. Um, in the ideal situation, you would pick something that travels directly overhead and you would observe it, say, directly at the zenith. And then if you want to explore your air mass correction coefficients, you can also monitor that same system as it goes closer and closer to the horizon, and that would allow you to, at least theoretically, derive those air mass correction coefficients. But I think the most important thing when it comes to picking a standard field is you want to have a relatively large number of stars in the field of view. You want to have a relatively large variety of colors within the field of view, and be able to observe it relatively often throughout the year. So if there's anything that's changed significantly, like you got a new camera, you got a new filters, you got a new telescope, or in the case of this last summer within the United States, we had a lot of fire smoke. Fire smoke, as you know, if you look through the sun at near sunset and there's fire smoke, you see it's very reddy orange as opposed to its normal yellow color. That's because all the blue light's getting scattered away. And so that fire smoke is still up there in the atmosphere that you're observing through. And so you'd want to redo your color transformations or rederive color transformation coefficients in that situation. Or even if you live in an area that has a lot of pollution, and a factory shuts down or a new factory starts up, and there's additional aerosols that are being put up into the atmosphere. Any of those things could result in changing your color transformation coefficients, and so you'd want to go look at them. So back to the topic of which fields should you use, I would try to pick some that you can see relatively frequently, or try several different ones and make sure that you're getting consistent color transformations between all of those different systems.
Great advice. Thank you. Okay, so a couple more questions here about color transformations, and we have one or two more topics before we'll be at the end of the list. So, do you know whether AIP for WIN includes color transformations? Quick question there.
I don't think it does, but we'd have to go read the manual.
Okay, good advice to go do that.
Yeah, and if I'm wrong, Richard Berry will set me right the next time I talk with him on the phone.
True, true. Okay, then we have a question here from John Hoot, who says that when you're using a one-shot color camera, of course, you're taking all of the bands simultaneously. Does this mean that you can use the instrumental color indices rather than the catalog color indices, and thus handle the color indices and chromatic effects simultaneously?
You might be able to do that. It really depends on what is the bandpass of the camera versus what is the bandpass of a green filter or a blue filter in the camera versus like the Johnson's cousin systems, for example. And so it might be possible, but if there's significant deviations between, say, like blue versus B, like as we saw earlier, a lot of the CMOS cameras, the color CMOS cameras, they often have a fairly large infrared leak. That could turn your B into basically a B plus R, or a B plus I, which doesn't correspond very well to a B, and it probably doesn't even match up with something that's in between. And so you have to be relatively cognizant of what is the specific transformation, sorry, what is the specific um, um, you know, uh, transmission characteristics or quantum efficiency of your camera as a function of wavelength, and have you put in place an infrared block filter, a UV-IR block filter even, that would take out some of these other effects that might be impacting the camera.
Right. Okay. Thank you. All right, next up, we have two questions about filters. So first from Patrick Kavanaugh,
Mhm.
why is it that you have chosen the Tokunaga filters? Patrick says he realizes he already mentioned this, but if you could
Mhm.
please elaborate in a little more detail.
Yeah, so those filters that sit out in the infrared, so these were the J, H, and K bands. There's been a variety of different filters. There was the Mauna Kea sets of JHK filters, and then actually there's probably like 4 or 5 different sets of JHK filters if you go back and you look in the literature. I believe those particular filters are relatively easily procurable. And it's a relatively new standard, like from 2002 or something like that. But the reason why those filters exist is because there are atmospheric band passes out at those particular wavelengths, and the filters attempt to maximize the amount of light that comes through in those regions. And so I would suggest that you go take a look at the paper that describes those filters, and I'm sure that they discuss not only the benefits of their filters but the detriments of previous filters that have existed.
Okay, thank you. All right, final question on filters here. This one comes from Don Selly, who asks about the possibility of using imaging RGB filters designed for astrophotography and actually transforming them to BVR. Is that reasonable to do?
Yeah, so the problem with red, green, blue is that you have to ask, what is red, green, blue? As you saw in the presentation there, two Sony sensors just from slightly different product lines had a 10% difference in green, not accounting for the huge infrared difference that they had. There are very tightly controlled green filters that exist out there. So they're like professional grade green filters that have very specifically defined band passes. But by and large, red, green, blue is not a standard. And I've got a couple of Raspberry Pi cameras on my shelf behind me here that they actually have a color correction matrix built into the camera itself that is programmed at the factory. And I have two adjacent or nearly adjacent serial number red, green, blue Raspberry Pi HQ cameras. They have different color correction matrices. Now, they're not widely different. They're just slightly different. And so I think the odds of having a set of standard stars for BGR to transform into Johnson Cousins red, green, blue is, or sorry, red, green, blue into Johnson Cousins BVR is probably unlikely because there's no standard definition of what blue means or what red means. So it's really going to be on a per system basis or even down to like a per camera basis. Um, Now, Lauren, I caught one more question that was over in the chat here. James Foster just asked if we were ever going to have like another follow-up campaign to what Arnie did a couple of years ago, which was to have people go out and look at standard fields and obtain do this color transformation campaign. And if I remember right, we did that not too long ago. I think George Silvis really led the charge on the forums to go out and do a transformation campaign. And I would encourage everybody, if you haven't gone out and observed those standard fields before, again, look at the fields that are listed on the AVSO's transform generator page. There's, I believe, 6 or 7 different standard fields, both in the northern and southern hemisphere that you could observe. Go out and look at them with your system and determine what your color transformation coefficients are going to be, because it really does improve the quality of your data. And so whether or not we'll have another, large spread campaign for doing, like color transformation week or a color transformation competition or something like that, I haven't decided yet, but that might be something that we do in the near future.
Excellent. Okay, thanks. All right, and with that, we are at the end of our questions. So time to go ahead and wrap up. Let me get that final screen share up here. And I'd like to go ahead and extend a heartfelt thank you to Brian for sharing his time and knowledge with us today. As I'm sure you saw in the chat, Brian, there's been quite an avalanche of people thanking you for an excellent presentation. I have to join in because this was maybe the best presented talk that I've seen in a very long time. So thank you.
Oh yeah, and thanks for everybody for attending, right? We put these webinar series together for your benefit. So if there's ever anything that you have any questions about and you want to know a little bit more about, we're happy to explore them. And I think in this situation, exploring like the why of color transformation was something that we hadn't really discussed, perhaps since Arnie's CCD school, maybe 15, 20 years ago. So I thought it was well worth our time to talk about it today.
Yes, very needed. Thank you. Okay, I would also like to thank again this webinar sponsor, Chroma Technology Corporation. Founded in 1991 as a 100% employee-owned company, Chroma Technology is a leading manufacturer and OEM supplier of highly precise optical filters using thin film coating technology. Chroma Technology stands out in the field of astronomy for its unparalleled expertise. Their optical filters are designed to not just meet, but to exceed industry standards, ensuring superior performance and durability for years to come. And I would also like to express our sincere gratitude to our 2024 series sponsor, Boyce Astro. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please check out their website to learn more about their work. Last but not least, I would like to thank everyone out there in the audience. If you watched, you listened, and you asked wonderful questions during today's webinar, we're so grateful that you were able to show up. It's your participation in all of our programs which allows us to keep growing, keep educating, and keep making an impact on variable star science. So thank you. We're so grateful for your support. Now, as a reminder, we do have a special mini-series that will begin airing next month, focusing on the AAVSO's special interest groups known as sections. The first one is scheduled for June 1st and will feature, among other sections, the solar observing section, who I'm sure will have some very interesting things to say about our ongoing solar storm. It's not something that you're going to want to miss. To register, please visit aavso.org/webinars, and you'll see this graphic with the registration link right next to it. I hope to see you there. Today's broadcast has been recorded, and if you would like to go back and reference the recording, you can find it on our Facebook page, where it will be automatically uploaded just as soon as we end the webinar. Pretty soon, we will also upload it to our YouTube channel, where we'll join an enormous library of educational videos, including those past broadcasts on the topic of applying transformations, which Brian had mentioned. You can find our library on YouTube by searching for the username AAVSOHQ. Now, when you log out of the webinar today, you should be automatically shown a survey. I would really appreciate it if you could please fill it out. Let us know what you thought and what we could do better next time. Okay, and to close, I would like to express one last huge thank you to Brian. Believe me, Brian, we appreciate you and everything that you do. Thank you.
Yeah, thanks, Lauren. I really appreciate this great webinar series that you put together for us. For those of you who don't know, Lauren is completely responsible for the whole webinar series. She picks the topics, she picks the speakers, she finds people, she brings them in. She does an absolutely wonderful job. And so, everybody, please give Lauren a great round of applause.
Oh, thank you, Brian. All right. See all of you next month.
Bye bye.